Hi, I'm Molly. All-pass filters are a feature available on all quantum consoles as part of the Mustard EQ. But why would you need an all-pass filter? Today we're going to have a look at what they do, where they might be useful, and have a listen ourselves. Before we get started, let's quickly cover a bit of terminology. Today our key word is phase. Phase is easiest to explain if we consider two sine waves of the same frequency. The two signals are in phase when their peaks and troughs line up, but out of phase when the peaks and troughs do not line up. The amount they are out of phase by is based on how far apart the cycles are and is usually measured in degrees. It's important to remember that phase is frequency dependent and is always relative, the difference between two signals, so it's irrelevant for a single isolated channel. Phase differences can be caused by time delays. Secondly, polarity. Most mixing consoles have what is commonly referred to as a phase button at the top of the channel strip. What this button really does is flip the polarity of the signal, so turns it upside down. Technically, this should really be called the polarity button, but is often called the phase button. Now, what does an all-pass filter do? As the name suggests, all-pass filters pass all frequencies at an equal level, but change only the phase at a given frequency. They are an integral part of building digital audio effects and commonly used when aligning PA systems, but they can also come in useful when mixing. The easiest real-world example to explain it is using a snare drum. When mixing drums, there are a lot of microphones picking up the snare drum. All of these microphones, snare top, snare bottom, overheads, will be at different distances away from the top skin of the snare drum, which is where the sound originates from, as it's where the drumstick hits. These distance differences ultimately cause delay, and therefore phase differences between all of the snare signals on the different microphones, resulting in both constructive and destructive interference across the frequency spectrum. This results in peaks and troughs over the frequency spectrum. Sometimes this can be improved by completely inverting the polarity of a signal, but this may just move the problem to another part of the frequency range. An all-pass filter allows you to focus in on a particular frequency and just change the phase there, fixing the interference issues instead of moving them. Our Mustard all-pass filter changes the phase 180 degrees around a centered point. The easiest way to understand how this is affecting the audio is if we listen with pink noise and have a look at the phase response. On the console, I have two channels of pink noise, both fed by the console's internal noise generator. When the channel faders are set to identical levels, I can flip the polarity of one channel and the signals will completely cancel each other out. Let's now introduce the Mustard all-pass filter. I'll turn the Mustard EQ on both channels. Turning on the Mustard processing strip introduces a small amount of latency, so in order to keep these signals phase coherent, I'll introduce this latency onto both channels. Both the green upper mid and the yellow lower mid Mustard EQ bands can be switched to be all-pass filters. This is done by pressing the band button. I'll switch the green upper mid band of the EQ on one of the channels to an all-pass filter. If we look at our phase graph, we can see that there's now a 180 degrees phase change centered around 1.6K. If you're not used to looking at phase graphs, this shows the phase relationship between two signals. In our example, where the line's flat, the signals are in phase with each other. We can tell this because the flat line sits at 0 degrees phase difference. Moving up the frequency spectrum, we can see that there is an increasing change in phase shift. the signals are becoming more out of phase, which can be seen as the line gets steeper. Above 1.6 kHz, the signals become more in phase until we get back to 0 degrees phase shift. I'm now going to change the frequency and the Q of the all-pass filter, and we can see how this phase change is moving around and becoming narrower and wider as I change the Q. Just to prove a point, I'm now going to solo the pink noise channels one at a time. Notice how there isn't an audible difference between the two. This is because the level of the signal across the whole frequency range is not affected by the all-pass filter, only the phase is. If you introduce the all-pass filter onto an isolated channel, you won't be able to hear a difference. This is because phase is always relative, so we need another similar signal to compare it to. It's all very well listening to pink noise here, but where can this be used in mixing? All-pass filters commonly help when there are multiple sound sources of the same signal causing destructive interference. Snare top and bottom, kick in and out, or bass DI and bass amp, to name a few. But also when there is spill between microphones. For example, snare spill onto the hi-hat channel, which is interacting with the snare drum channel. It could also be used for issues with destructive interference between different instruments, like the kick and bass guitar. Sometimes the resonant frequency of the kick drum can cancel out with the bass guitar. This could be improved by inserting an all-pass filter onto the bass channel and tuning it to the resonant frequency of the kick drum. Let's have a listen to a practical audio demonstration. I've got a drum loop here, and for the purpose of this example, we're going to be comparing the snare top and the hi-hat channels. I'm going to fade between the two channels so we can hear how they are interacting with each other. When both faders are up, we're losing a lot of the low end of the snare. I've got 3 snapshots here. When I fire the next snapshot, that's going to change the polarity of the snare top. So let's compare those two. With the polarity inversion, we're now getting the low end of the snare, but we're losing the top end. We haven't solved the problem, we've just moved the problem. My next snapshot introduces an all-pass filter to the snare top. Let's have a listen to that. This is now introducing more of the low end, but we're still keeping the high end. I'll flip through the 3 snapshots so we can compare them. Today, we've looked into the science behind all-pass filters, explored some of the possibilities of where they could come in useful, and had a listen. Next time you're on a Quantum console, why not have a play around with the all-pass filters to see just how useful they can be for your own mixing? Head over to YouTube to find more videos on our Quantum Theory series.